Cool. So I'm Chris. It's Ted. We were Thayer School of Engineering students. That's kind of where we did this project. But we were sponsored by Siege Technologies. Dan and Jason are in the audience if you want to hear more about Siege. So basically, our work was kind of exploring automotive cans. We looked into kind of the networks that are on cars and kind of how to get access to them. So we thought we'd start off with a short little video kind of showing what you can do once you get access to the car.
And there's no audio, unfortunately, but we're revving the engine right here, and then you can see we were able to fake the speedometer reading. So it's a pretty sweet denial of view attack. And also, you don't have audio here, but we found a packet sequence that will actually lock the doors on one of the CAN networks, lock or unlock, depending on the state of the vehicle.
Yeah, so now we're going to kind of jump back a little bit and kind of tell you how we got there and how you guys could get there if you're interested. So the project was part of a Thayer School of Engineering capstone project. It's a course that kind of pairs you with an industry sponsor who has an idea for development. So, I mean, any of you guys are out there looking for some cheap labor, it's a cool thing to look into. Our sponsor was Siege Technologies. These guys are a private R&D firm focusing on cybersecurity, cyber warfare. And they kind of came up with this idea of looking into automotive security in the CAN bus. As I said, Dan and Jason are in the audience if you want to learn more about what they do. Automotive security was kind of the topic of what we were supposed to look into, and with a focus on the CAN network. So we kind of broke that into two things we wanted to do. We wanted to prove that there was a vulnerability there, that there was security risk, as well as develop tools to kind of allow people to replicate our work and build on it. So we went and hacked a car, as you can see, and then we developed kind of a loose methodology that kind of would help somebody kind of easily go about repeating it, as well as provided a software package so you can kind of just easily jump on the bus without any kind of the embedded systems complications.
Cool. So a little bit about the team. I'm Ted, and I sort of had some background in embedded systems, computer architecture kind of stuff. Chris was a software engineer. He had some Python experience, higher level stuff. Grayson basically wanted to build Stuxnet, was his approach to the project. So the advantage of students, you get cheap labor and you kind of get yahoos at the same time. So that was fun. So we graduated. That's the sort of surprise ending to the story as we passed. I'm working at Automatic, which is a small automotive-based startup out in San Francisco. And then I'm going to go to the Grasp Lab at Penn to get a master's in the fall. Chris is going to Microsoft, and Grayson is heading to Motive, which is a small EV startup out in the Bay Area. So actually, two of the three of us wound up doing car-related stuff, which is pretty sweet. None of us had any background in car networks at all when we started. So just to go over the goals again really quickly, it was reverse engineer a vehicle, build tools for muggles, something that people didn't have to have a background in networks to sort of jump into and start playing around with. And then we had to explain it all to a review board of mechanical engineers in order to pass, so that was kind of fun. We had to definitely get good at explaining it to people who didn't necessarily have a background in it. So to start off, when you think about cars, well, what is a car? Most people, when they think about vehicles, think about four wheels and an engine. You have a steering wheel and you have brakes. You have gas pedal. It's a mechanical system, and it gets you from point A to point B. And then these days, cars have all these crazy things layered on top of them, like GPS or dashboard displays, keyless entry. And people don't really think about that. But the truth is, cars are a whole lot smarter than you would think. There's a lot more going on under the hood, so to speak. If you look at a car today, it's actually a complex, highly connected network. You have all these components that are speaking to each other. If you think about it, you get in your car, you start driving. When you get above 10 miles an hour, your car doors lock. How does that happen? These components are communicating with each other. And the way that they do that most frequently these days is over the CAN, which is Controller Area Network. It's a low-level network protocol that was specified by Bosch in about 1986. It's part of the OBD2 maintenance standard, so you can access it really easily via a port that's in every vehicle since 1996. It started appearing in cars around 2003. It was actually mandated in 2008. So any vehicle sold in the US since 2008 is on CAN protocol. And then it's actually a really popular protocol. So there are a number of sort of sub-protocols that are used in automation in industry, including TT-CAN, CAN-Open. But we were dealing primarily with automotive CAN. For embedded or network people among you, it's a multi-master broadcast network, meaning that every node can talk at any time. and it handles conflict resolution with bitwise arbitration. So higher priority nodes talk, and lower priority nodes will back off and send the message later. Really critically, that means that all nodes receive all messages, so you don't have to do any kind of addressing. You just send a message on the network, and anyone who wants to interpret it will interpret that packet. It's also optimized for speed and reliability, not security. These are generally assumed to be closed-off buses, and so there's very little, if any, authentication on messages that are sent, which makes them super easy to hack. It's really fun. And then lastly, it's worth noting that they're really short messages. The data payload of any individual packet is between 0 and 8 bytes. It's really intended to sort of chirp sensor data around the network, not for lengthier communications. The syntax becomes really awkward when you have to send longer messages. So the useful analogy that we came up with is basically, this is the central nervous system of the car. It's used to report sensor readings back from various points and sort of coordinate all the stuff that's going on within the body. And then really quickly, just look at an individual CAN packet. The 3 parts that we cared about were the arbitration ID, which identifies the node that's sending the packet. So we refer to them as ARB IDs throughout this presentation. And again, that also determines the priority. So a lower ARB ID actually has higher priority on the network. The DLC, which sort of specifies the format and type of the message that's being sent, as well as the length, and then the data payload itself, which is up to 8 bytes. And then there's a ton of error checking, CRCs, the whole 9 yards, to make sure that all the messages are getting sent out properly.
Cool. So kind of a brief overview of what you could do if you wanted to go buy some software packages to do this kind of analysis. At the high level, you can get licensed by a manufacturer and get some high-end tools that allow you to kind of go directly into the ECUs, reflash them, reprogram them. But they are in the kind of the $10,000 to $50,000 range, so it's out of our budget. Mid-range, you can get some kind of custom oscope apparatuses. You can also get high-end diagnostics tools. This is kind of what your mechanic might have. These allow you to kind of see the baseline statistics, kind of how fast you're going, what your miles per gallon is, what your diagnostics codes are. So if you get a check engine light, this is what they'll check. One notable one is the one at the top here is the microchip CAN analyzer. It's designed for kind of people developing their own CAN networks. So it allows you to actually see the packets on the bus. But it doesn't really have a lot of customization. You can't really get into the bus and kind of fool around and have some fun. So that's kind of a big limitation, or it was for us. Kind of on the other side of kind of what you can do with the CAN buses and whether they're secure in cars, there's a lot of hobbyists out there. You can find a lot of blogs with people trying to do this kind of thing. But it tends to be pretty scattered, not really well documented. There's not really a go-to source if you want to go, get on the bus and look at it. There's the Canduino. It's an Arduino shield. Academics, there's the Center for Automotive Embedded System Security. These guys have actually done some really cool work. They proved a lot of vulnerabilities and kind of tried to get in and mess with cars on a lot of different surfaces, including Bluetooth. Kind of from our standpoint and your guys' standpoint, they purposely omitted all the crucial details. They don't release any code. So you can't really take their code and go and verify it or have some fun. So we thought that was not fun at all. So our goal kind of became to release the code for you guys.
So we worked as part of the Good FET framework, which has been developed by Travis Goodspeed and Andrew Ryder. We were working with the GoodThopter 10, which is the new member of the Good FET family. It's been described as a sexy Good FET CAN device by certain friendly neighbors. The mechanical engineers were all sort of horrified that this little chip was our final 6-month project, but we actually grew to love it. So it sits between your sort of client Python code and then the CAN bus on the car. And more specifically, it's actually a MSP430, which interfaces with an MCP2515 CAN chip. The MSP430 right now is really just sort of a dumb SPI relay. You use it to configure the CAN timing. You basically write directly to the registers on the CAN chip. So you configure it for timing, and you can filter for stuff, and then actually read and write CAN packets. The one disadvantage of the firmware, the way it's written now, is that it's pretty slow. So one of the sort of ongoing projects is to rewrite the firmware pretty simply to get it on an interrupt-driven, and then probably buffer flushing from the MSP430 back to the client computer. So the CAN chip is nice. It's got hardware filtering, and then it has these hardware interrupts, which we haven't implemented yet, but are planning on shortly. And so if you look at a packet that you get off the chip, you can see it has a standard ID and then potentially an extended ID, the data length code, and then the actual data payload of the message. So this is what we were pulling off the chip. So armed with this little piece of hardware, we went out into the world and we bought a car, which was super fun and exciting and scary. And so we went online. There's a lot of information online about what vehicles implement what protocols. So we found that Ford started implementing the CAN protocol in about 2003, 2004. So we picked up a 2003 Ford Focus and hooked up to it and started reading packets off. On the left, you can see the packets that we were pulling off, and the right, sort of our experimental setup. You can see the GoodThopter hanging out there. And we started looking at these packets, and we were like, sweet, we're going to do some analysis, and we sort of were like, all right, we're going to understand these packets and like learn some stuff about the state of the car based on them. And we pretty quickly realized that we didn't understand what the heck was going on. They didn't seem to make any sense. The DLC didn't correlate to the length of the packets. Data was kind of complete noise. So none of us had done networks before. My reaction was like, wow, stuff's tricky, man. Like, I don't know what's going on. The truth was, it's not that tricky. We bought a car that didn't use CAN. Yeah. It was not our finest moment. Our advisors weren't super stoked. That was a dark, we sat in the lab, we were like looking at this, I was like, oh my god, there's an older Ford protocol that's like totally different, that's not CAN at all, that's OBD2. We definitely fucked that one up. So it wasn't great. Anyway, the nice part about being in an academic environment and buying cheap cars is you can go to your advisors and beg and plead. So we learned a nice lesson from that, which is this is an OBD2 compliant protocol. There are a lot of OBD2 compliant protocols. And it just so happens that the specific pinout on the OBD2 port will tell you what protocol your vehicle uses. So you should always just double check the pinout on that thing before you get a car. Don't trust what you find online because the information online is not reliable about this kind of stuff. And then the second thing that really threw us for a loop is there are two kinds of RS-232 to CAN cables with different pinouts. And the one that we had actually routed the J1850 pins to the CAN pins. So when we connected, we were able to pull data off, but it was like total junk. So watch out for that one. That's a good lesson to learn. And anyway, our advisors were very understanding, and we managed to sell that car and get another cheap car. So the project was able to continue, thankfully, with a slight delay. So now we're going to actually talk about what we did.
Cool. So as soon as we bought the right car with CAN, we were able to kind of immediately start pulling off packets and see what was on the bus. However, almost immediately we realized that we didn't really have a good tool to look at the data. We're pretty much just dumping it all to the terminal, and this data was flying by us at several hundred packets a second. So kind of what began as a tool for us to kind of organize ourselves ended up being a fairly big project, was the data management, kind of a user interface to allow people to kind of jump on this bus and work on it. So kind of a quick, high-level diagram of kind of how our software is laid out. We really wanted to make it so that us in the future users could really kind of jump in at any level. So we could get the low-level embedded systems guys could help us rewrite the SPI communication, make that faster, optimize that. In the middle, you could have somebody really interested in kind of analysis tools, and then at the top, you have Python, a Python GUI that we wrote in tkinter. So you could have somebody come in there and really flush that out and make that good. So what you have is at the bottom, you have this basically this list of subclasses, starting with the raw CAN communication. Basically outlines the very simple read-write capabilities, error analysis, the digital logic. Below that, we have a subclass that allows for the generic analysis tools. So this is kind of, we built some very simple experimental methods, like packet, receive, and response, some fuzzing, things like that. And then kind of at the bottom, since all of these protocols end up being very car-specific down to the year and the model, we really thought that a user is going to want to have their own custom model that they can integrate both to our GUI and to the code base. So there's a layout and a framework for kind of adding your own code and kind of building on it without modifying a lot of stuff, which is good. So then kind of there's this nice user interface, which really allows, so like with the network being kind of unprotected, once we saw packets, the easiest way to kind of make correlations was just kind of create a user interface that allowed us to see the changes on the communication in real time. Because unlike a lot of like networks where you're receiving packets and sending them back out, the response for a lot of things is physical. So you have to be sitting in the car, opening the doors, revving the engine, changing the gears. And so the user interface really helps you to kind of sense what's going on, visually, and then also see it on the monitor. So kind of before we show you it, kind of the key features, we integrated the logging with MySQL. So there was a bunch of us working on the project, which is why it's not SQLite. We might change it over. And that allows us to kind of put it all in a big database, do some analysis later on. There's a lot of sniffing options. You can sniff for different filters. You can also set the length of time you listen, tag it so that you can look at it later. Custom packet injection, so you can kind of fool around with that, as well as the methods. There's a documentation window, which allows you to kind of easily kind of take notes and store packets. So one of our current works is to kind of rewrite some of this using Scapy so that the networks guys can understand what we're talking about, as well as it really allows it to be a little bit more organized and allow for easier manipulation. So as that stands, we have most of the protocol laid out. We're just yet to integrate it with the database. So we also thought we'd give you kind of a quick video that demonstrates how the user interface works. It's by no means like a comprehensive demonstration, but it does kind of hopefully show how easy it is to use. So starting with the basic communication, we have you can just kind of write in your IDs, your bytes you want to write in. You can sniff, as well as you can set filters. So these are just setting the IDs you want to listen to. And then give you a quick demo of sniffing. So you can set the time to listen for. And then basically there's two displays. One is just a rolling display that'll show all the packets as it reads it in. The other is this nifty fixed display, which each ID has its own line and it's updated in line. So you can kind of see how each message is changing with time. And that kind of helps you notice like speedometer changes. You can also filter by an ID. So if you notice that one ID is correlated to kind of everything with driving, you can look at only that and ignore all the background traffic, or up to 6. We also, as I said, have a SQL database, so you can store it, and we've automated kind of uploading it to these databases. And then this is just SQL Pro. It's an open source. And this just kind of shows that we've broken it apart a little bit so that you can search and filter and do some analysis. You know, timestamps, the ID, the data bytes, the length, comments of when you took it, things like that to really kind of help the post-analysis. So moving on to the experimentation, as I said, we've built some fairly basic experimentation methods, but they allow you to kind of get on the bus and do some really fun stuff right away. One just kind of being fuzzing, where we're injecting kind of randomly formatted packets that are with given IDs that you can put in, and this causes some chaos pretty much right away, which if you want to freak some people out, you can have fun with. But then once you kind of get down to it and really want to learn about how these protocols are communicating, there's this like documentation window. It's just kind of displaying a JSON database, and you can store packets in this, which is kind of nifty, so that you can, by just clicking on it, you can re-inject it back onto the bus. So you can store them, save them for when you want to use them and see how the car reacts. Finally is this custom car module. So this can be entirely separate files, and you can just kind of link it in the settings. And here we kind of built out one for our car that allows for diagnostics. So I don't know if you can see, but it's kind of reading out basically the RPMs and the speed at the moment. And then you can do fun denial of views where, again, we don't have sound, but we're revving the engine up as hard as it goes, and it's just showing the tachometer is 0. Likewise with the speedometer, here we're just going to set it to 60, and we're sitting in the parking lot. So you can have fun with this, and you could, if you wanted, leave it on there and drive around and have everything just go haywire. And all of this is fairly simple to do. We just kind of played around for a little bit once we got all the code working.
Yeah, so this was sort of, we like to call it reverse engineering the CAN bus, aka explaining hacking to mechanical engineers. So in our case, the incentive was actually graduating from college, but you can pick your own incentive. And so basically, we're going to walk you really quickly through how you can use this tool, get on the bus, and start playing around and figure it out, and sort of walk you through how we did it with one particular ID. So we came up with all these fancy names, like passive listening, physical stimuli, active probing. Grayson was like a scientist, and so he wanted to couch all this in like really legit terms. But basically, we sniffed the car, we poked the car, and then we started writing stuff to the bus. And turns out that works. So I mentioned speed problems earlier. This is actually sort of the biggest issue through our project, is that our firmware is pretty slow right now. So we're only able to get about 1/10 of the traffic on the bus, so every like 10 packets or so. So we started with unfiltered sniff, and we realized that we were not getting all the traffic. So we did an arbitration ID sweep. There's only 11 bits in an arbitration ID on a standard network. So we're actually able to listen to every possible ID and find all of them. And then we went and did a filtered sniff on each of those to sort of characterize their standard traffic and all that. And so we're going to talk about ID 201 because that turned out to be a really interesting packet. And so ID 201 broadcast at like 60 packets a second, and it had this pretty standard format. We noted there were 2 varying data bytes. So once you have an ID that you're interested in, you can start doing fun stuff to the car. We call these system perturbations, which basically means like driving the car around or turning the lights on and off, that kind of stuff. And then you see what happens on the network. And so we noticed with 201 that revving the engine caused certain data bytes to increase, and then when we were driving around, we saw data byte 4 started increasing. And so that was when we were like, all right, let's go back and try messing with this. So we started fuzzing on those particular data bytes, and we saw that when we fuzzed on data byte 0 and 1, the tachometer started shifting, and data byte 4 seemed to control the speedometer. So that's when you can go back and you can actually start injecting specific packets with specific values and sort of get a better idea of what exactly is going on the bus. And so we were able to map out data byte 4 and figure out, okay, this thing controls the dashboard display for the speedometer. If you want the speedometer to read a specific value, here's the value that you inject. And then once you've sort of reached that level of understanding, you can do all kinds of fun stuff. I wrote a little script that like looks for packets from ID 201, reads in the data byte 4 value, modifies it, and then blasts it back out. So you can make the car look like it's traveling 15 miles an hour slower than it actually is. Fun stuff like that. And so that's sort of like the really quick, like, you hop on the network, you start playing around with it. You can do all of this with the GUI that we built. You don't actually really need to understand what's going on in terms of the CAN protocol. So yeah, super fun. And then once you have this kind of understanding, you can build your own custom module on top of what we've built and really just have quick access to all that. And then just to give you an idea of what a fully mapped out higher level protocol looks like, ID 420 actually, when it blasts out, is telling you all kinds of information about the current state of the engine. Pretty sweet.
Cool. So kind of coming back to that microchip that we talked about earlier, we thought it would be kind of nice to kind of show you why you'd want to use our software instead of its. So we kind of broke it out to a few different categories to kind of show you where ours was better or worse. As we mentioned earlier, ours is a little bit slow, but this is pretty low-hanging fruit. We just didn't really have time to really get into it yet. But where it does really exceed is its customization. The microchip one really only allows you to kind of write single packets. You can't get in and do like packet listening and response. You can't do a lot of the custom attacks that you really want to do.
Also, it costs $100.
Yeah, it's also $100, and the good FET board, you can talk to Travis. So in the conclusion, all you need, and you should want to get on the bus, is just this board and then the software, which we're going to tell you how to get. So
we highly encourage you to get on the CAN bus. Your ticket to the bus is the GoodFet 12. You can get it as part of the GoodFet framework. Email Travis your complete mailing address. Don't ask for permission. He doesn't want round trips. Just send him your address, number of boards you want, and he'll get them to you. And then you have to get the components and solder it yourself, but that's not too bad. And then, of course, the code is all open source goodness. It's on the GoodFet repo, and then we have a particular folder that's actually labeled REcon. It's also got a bunch of documentation on the CAN protocol, which we found helpful to get you up to speed. You need a couple Python packages, nothing too bad. MySQLDB is sort of the biggest and most annoying one, but we actually just made that optional in case you're not trying to hook back up to that. In terms of work that's going on in the project right now, I think the coolest and what I want to do the most is work on the MSP 430 firmware. It really shouldn't be a big deal. It's basically getting interrupt driven and then putting a buffer in and then flushing that buffer back to the computer, as I said, and that should get us up to speed really fast. We're also interested in reverse engineering more manufacturers' higher-level protocols, which basically means listening to more cars. So if you have a car, you could help us out with that. Or if you don't and you feel like borrowing your friend's car. But don't tell them I said that. We'd also like to build in support for ISO-mandated PIDs. This is basically the standard. There's a standard scan tool ISO format, so you can request a ton of data from any vehicle and it'll respond to you. And if you're interested, there's a Wikipedia article which outlines all of that. So that really won't be hard. It's just sort of testing it and make sure it works. Then right now, as Chris mentioned, we're integrating with Scapy. Riverloop Security, specifically a neighbor named Ryan Spears, who's awesome, has been helping us out with that. So that's ongoing. I did want to toss in a couple caveats with this. The first is that some manufacturers implement segmented buses, meaning that there are multiple networks on your car. And so even if you have access to the main CAN network, you may not have access to sub-networks. There's also other protocols that are in use today. FlexRay is one of them. It's probably the best example. It's used in expensive German cars, particularly the BMW like 3, 5, and 7 series. The 7 series is almost entirely on FlexRay, although it does still have a CAN bus. But because it's more expensive, its use is relatively limited. Then there's LIN, which is used for other chassis. But it's not as sort of flexible or open-ended as the CAN protocol. One other caveat, which I really should have put on here, which I didn't, is do be careful. Don't fuzz your car when you're driving. It's a little hard to drive and distracting when your speedometer's going crazy, stuff like that. Also, one of the reasons that we put fuzzing all the way at the bottom of the list is that fuzzing randomly on random RBIDs can have unknown impacts on your car. We didn't actually break anything in our vehicle during testing, but some of the AutoSec papers mentioned that they did throw an ECU into some really random state, which they had trouble getting it out of. I wouldn't worry too much about it if you aren't truly randomly fuzzing, but just a heads up. And then thanks. We have lots of thanks. First of all, Siege Technologies, Dan, who particularly worked with us, Jason, who agreed to sponsor the project. It was a lot of fun. And then our advisors, Professor Sergey Bradas, Professor Vincent Burke back at Thayer, a bunch of friendly neighbors, Travis, Andrew, Ryan. And we'd also like to apologize to the Thayer School of Engineering if anyone from there winds up watching this, because we did park a sort of dead auto in the parking lot for a while. and they were nice about that. Sweet. Okay, so that's our presentation. We're going to turn things over to Craig for a little bit, and then we're going to do a combined Q&A at the end.